silicon carbide nitride. This is an emerging technology altogether. What happens? This is ceramic material. Ceramic materials, sure, they're very investigated. We know lots of ceramics, but not as much as we should like. What is the good part of that is that this material could be generated, could be made from a liquid precursor. I have a silicon-based polymer in liquid phase, and I could mold it in any shape I want. That works fine. There is a process following that of pyrolysis. I mean, it's cross-linking and pyrolysis, and then that means heating without oxygen. And I get a ceramic. The point is that ceramic shrinks about 30%. And I say about because you don't know exactly how much. Every time the batch is different from the polymer, you get a different number. So how you go through that? Now, tell you something. This silicon plastic polymer is not intended for silicon carbide nitride high temperature sensors. It's made for composite material. So one has to go into that technology and improve the processing for this polymer to the extent that the technology yields same product every batch. Now, this from cross-linking. Cross-linking is the first process in which the atoms that are a long chain of molecules, they will interlace. They will create a kind of interconnection between atoms that it will be hard to remove them. And then pyrolysis will modify that shape from that bonds of that type in specific bonds only in which you'll find only silicon, carbide, and nitride. Hydrogen is all removed, completely removed from the structure by the gasification through heating at high temperature. The process is long. It's about 28 hours as per today. But again, this could be probably worked out somehow. The structure at the end, it's a full array. What is a full array? It's a perfectly geometric structure in which there is no room for atoms. So if, oxygen is tricky, would get anywhere. So if, say, we have a weak bond here somewhere, oxygen would be happy just to remove that atom and stick it. But in a full array, that is not possible. We have graphene, full arrays, graphite carbon, right? Like carbon nanotubes, but full arrays of carbon, or silicon carbide nitride of the same time. What is the point? They don't oxidize. Now what happens with a thin sheet of metal exposed at 1,000 degrees? Will oxidize and then expose again, oxidize more, and eventually will just go through, right? They will oxidize completely. You might say, yeah, but it's some... I think more or less this is what will happen, whereas a full array would not do that. Full array would not oxidize it. So that is a very good positive point. Moreover, material is not softening up to 1,900 degrees. We checked. It has some ferromagnetic properties. They don't change up to 1,400 degrees. And conductivity remains pretty same. It has high resistance, but from the mechanical point of view, softening again occurs at 1,900 degrees, and hardness goes to 37 gigapascal, which is quite high. Diameter is 35. Now, if in this structure we add ions, then this material becomes a supraparamagnetic. You might say, what is that? This makes the material to encounter a magnetic pole. It's like a spin. So each atom inside will have a different magnetic orientation. That means the material itself could be organized, reorganized, as we have in amorphous, reorganized in crystals. If we have one single large crystal, we'll make it a silicon-like material, a semiconductor. I mean, That work so far led to 5 to 7 microns crystals, but it's room to go further to increase them. Probably it's not this way to increase the crystal, but through thermal annealing. Heat it up, cool it slowly, heat it up, cool it slowly, and you get this crystal sludge. So that would be we'll discuss about spintronic a little later. Technologies for packaging sensors 800 degrees, they are more or less available. I mean, from the optical fiber, is there, that could be definitely used. However, the fabrication technology I just mentioned is not robust enough. There are a few groups in the world working on that. This is very beginning. This is a technology that it's very beginning. Now, according to that, there are lots of investigations now, and for example, there are people working on silicon nitride aluminum, which is also ceramic and has similar properties. So the field of material is still large open for high temperature applications. This is a sheet of the product. It's intended to be a temperature sensor for very high application, made from silicon carbide nitride. But what happens, it happened that we met in a NATO meeting, the CEO of this company, and they, mentioned that they don't have the product. That was just an intention, right? Product is still far away from being ready. Spintronics is the point. In that, if we have a monocrystal in silicon carbide, and in each atom here we could have a different spin, one electron could modify the spin. So that means one could build electronics for one microelectronics for one electron. At this stage, we need a current. We need a current from the emitter and open the gate to have it away through the collector. We need a current. We need some number of electrons. Spintronic would be an electronics in which one electron will give you a bit of information. Advancement in photonics, one photon. It's a little bit more advanced, the technology in there. I mean, there are lots of integrations into one photon detection. Spintronic is still a dream, in the sense that, for example, if I can turn the spin and maintain it for whatever reason, I could use memories, I could build memories. Layers of silicon carbide, memories of quantification was like 1 terabyte per centimeter squared. So that would be significant contribution to information technology. Moreover, if these properties would not change at high temperature, electronics would be built. Electronics operating at 800, 900, up to 1,300. That would be something indeed remarkable. Again, who's going to be investing into that? Optical MEMS technology is basically...
What's the actual material that exhibits the spintronic?
Silicon carbide nitride is one of them.
Oh.
Apparently, silicon nitride is also doing that. But it has to be annealed in a certain way. I mean, if you get a monocrystal, that will do. Spintronic is just a dream. It's not yet set in. Optical technologies, okay, so basically the applications will look at the temperature distribution, gas composition distribution, eventually spectral analysis. What is spectral analysis? I send a bandwidth of light into a gas or something, and the gas will absorb certain frequencies because we like those frequencies. And when I read on the other side, I read a signature. From the signature, I could extract what type of gases I have, how much of each. And these are principal aspects of it. Now, that could be done. It's done at this stage in micro level for bio applications. There are spectrometers for bio applications, MEMS-based technologies. Now, the issue is that it's a long way to drag them to aerospace technology because there will be no pull into there. Optical MEMS. At the beginning, I would say when this optical MEMS came and say, no, we can do optical directly on circuits, we don't need this trouble wait for MEMS. It's necessary to think in terms of MEMS because on MEMS one could build mirrors, it could be attenuators, filters, directly on the circuit. So that is a big advantage. Processing them electronically brings noise and serious problems. However, you recall that failure has an optical interface at this stage. This failure that we have right now implemented on aircraft. As a principle of operating of this optical switches, for example, a mirror would basically deviate the normal track of the light from one direction to another, and based on whatever data, this could be encoded somehow and produced as an information, bit of information. This is an example of a spectroscope made in Hamatsu, made in Japan. And the application of that would be basically in anywhere where we don't have direct access to intervene with a sensor, but we could eventually have access to, send information, light, bandwidth of light spectrum, and detect it at the other end. It's not simple. And they say, oh, it's simple. You just inject there some light and you measure what you have at the other side. It's still a long way to get in there. We talk about spectrum is one. I have to have a large bandwidth. Now, at low temperature, my spectrum would be towards blue. High temperature spectrum will be towards red. How do I do that? Either I have various sources of light, or I have what is called a tunable diode. Diodes, light diodes, could be tuned from one color to the other. You probably saw this there in the commercial things, lights that they go from yellow to red to blue, and they continuously do that. These are the diodes. Sure, that's commercial products, just to whatever truck, but they could be used very, very well, definitely, for detection of various physical quantities in the air.
Question on that. Is that fairly far along, this technology for aerospace?
I don't think it's far along. The point is just that someone has to decide to implement it. If you build a new engine, right? You decide upon the technologies that you are going to use. Are you going to include this one? It's not on the desk. You have to put a little bit of money to adapt it. So that is always the issue.
One of the big problems with tunable diode lasers, they are quite temperature sensitive.
All optics are temperature sensitive.
So they definitely can't be put somewhere.
But you have the advantage. You could pull optical fiber, could they move them away. However, engine is not a friendly environment anywhere. If you go outside, it's too cold. If you go inside, it's too hot. Right? It's very hard to find a place where it's comfortable.
Companies like Zoho that do this, but I was just curious if it's actually used.
Right. There are companies in Montreal doing that. They do, custom design sensors, optical sensors, so for any purpose.
We use it on testing.
Right, on testing. Yeah, I know, for an example, that they look into the plume here, and they check what is out. If you say have too much iron, that probably you burn the chamber, right? Something. So, there are ways to look into that. Right? But sure, you don't do that in flight.
Your land-based. It's impossible.